Yeah, it works. Hi guys. So just before I introduce my talk, I've got this little representation of a physical thing, like a real world example. So this talk is about theoretical physics. So it's always nice to ground it in a real thing, especially being amateur astronomers. So this is it's actually a video of R. Doradus taken using ALMA. That's a telescope in Chile, in the Atacama Desert. And what you'll see are bubbles that are 75 times the size of the sun, appearing on the surface before then going back under. It's basically convection on another star that's been observed. So stars usually see them as little points of light, but with this, you can actually resolve the surface of the star, and you can see this convection in action. So here we go. Can you see that? It looks a bit weird. You possibly can't quite make out what's happening, but that is what's happening, I can assure you. And this is actually a low mass star. I was looking at high mass stars, or as they're called, massive stars. So this is my talk, modelling massive star evolution. So I just to give you an idea of what we're talking about, I did a project over the summer. And that was about testing the impact of testing the impact of time-dependent convection in MESA simulations of massive stars. There's a lot to unpack there, so I will be unpacking every little phrase within that big title there, and I'll start with what massive stars are. And also massive star evolution. So obviously with stars we usually hopefully most of you will know that we start with a dust cloud. So a dust cloud like this one, this is called the Brick. It's a dust cloud that's near the centre of our Milky Way. So when stars are born, they're born in these regions of dust and gas that are quite dense. So with high mass stars, or these massive stars, when I say massive stars, by the way, I mean stars that are around 8 or more times the mass of our sun. So not our sun, but things that are much bigger. And this is near the centre of our galaxy. It's 26,000 light years from Earth, and about 100,000 solar masses. So that's 100,000 times the mass of our sun. And it's a small area for that mass. So scientists predict that massive stars will be born within this region. So one day it could be one of the most massive clusters in our galaxy. So that's why this is an image from JWST, and that's why people are investigating at the moment. That's why it's of interest. So next we get to the pre-main sequence, or as it's also known, pre-ZAMS. ZAMS stands for Zero Age Main Sequence. This is actually a low mass star. It's called NWC 758. But what's mainly important here is that you can see the star in the middle, and then this kind of bubble that's radiated out. So when a star is born, it creates this bubble within the region. It also can set off other stars being born, that kind of thing. And the problem with massive stars is that evolution is always much faster than low mass stars. So it's much less likely to find a pre-ZAMS star that's a massive star than a low mass star. So that's why I've got this example here. And that was imaged by ALMA, and it's a star in Taurus. Next we've got main sequence. You might recognise that. It's our sun. It's a great image. It goes. The main sequence ranges from ZAMS, which is zero age main sequence, to TAMS, or terminal age main sequence. Great names. Now, the reason why I say that is because on diagrams later on, it's very useful, especially ZAMS. It's very characteristic, the shape that it makes on the Hirschi and Russell diagram. If you don't know what that is, I'll show you later on. But yeah, so that is the main sequence. It's the longest stage of our evolution, but everything after that is very quick. So as soon as you get through this stage, it kind of goes so quickly, in fact, that it's very difficult to get an image. So I'm going to show some diagrams now. Now this is a very simplistic view of what of star evolution. Now there's a lot of particle physics that I could talk about, I'm not going to do that because A, I don't have time, and B, I don't want to review my lecture notes. So if you're going to ask me a question, I'm not going to answer. Anyway, but this is the general picture. So we've got hydrogen to start off with. Now, I say this is already an oversimplification because stars actually appear in 3 population types. We've got population 1, which are high metallicity. Now, metallicity in astronomy, so in chemistry, you might have, this region of the periodic table are metals. Well, for astronomers, it's basically all of it, apart from hydrogen and helium. So it's everything apart from hydrogen and helium. There are some other elements in there, basically, and those other elements are from the old stars that this star formed from. So from that star-forming region. And then the star exploded, it created some gas and dust. Then when that creates another star, then those metals are what forms that star. So there are other elements other than hydrogen and helium. Then we've got population 2, which is low metallicity. So that's maybe a 2nd generation or 3rd generation star. So that's a star that's been born from a star which was born at the start of the universe, for example. And then we've got population 3, which are no metals at all. Now, this is kind of something that's not really been observed yet. So it's more a theoretical thing, but it's probably something that there are out there. And I've been looking at 20 solar mass stars in the simulations that I ran over the summer. So the numbers that I'll be showing on the screen are to do with 20 solar mass. They're not to do with all massive stars. Because massive stars, they vary quite a lot in terms of what goes on. If you go to 25 solar mass or 15, they're all very different. Anyway, so after hydrogen, we get helium. So hydrogen burns. It burns via things like the PP chain reaction you might have heard of. That's probably what's going on here at the moment because we just get helium. And that takes about 10 to the 7 years. So that's what 10 million years, exactly. So yeah, we've got 10 million years for the sun. It's actually 10 to the 10 years, so already timescales are different. It's a shorter evolution to do that. Then the next stage, we get a carbon and oxygen core. So the helium burns into carbon and oxygen. We get a bit of some things like the CNO cycle you might have heard of. Again, if you're interested in these, look them up. I'm not going to go through them. But the general gist is we get helium, and then that goes to carbon and oxygen to make that core, and that takes about 1 million years. Okay, so shorter again. The next stage, these are general stages, by the way. There's I will show you it's a lot more nuanced than this, but also it's not to scale as well. That's very important. These central regions are very, very small. The hydrogen shell, as we like to call it, is enormous. So yeah. We've got oxygen, neon, and magnesium. So carbon goes to neon and magnesium, bringing 2 carbons together in a roundabout way, and that takes about 1,000 years to happen. Next stage here, we get oxygen we get neon going to oxygen. This is via alpha capture and photodisintegration. So alpha capture. Your helium, it's just a nucleus of helium, and then so an isotope would capture that to become heavier. Photodisintegration, instead, we capture a photon, so then it excites, it gains energy, and therefore it can change into a new isotope. So that takes about 3 years. So very, very, very quick indeed. It's very unlikely that you're going to capture a star from that. But also, remember, this is happening in the middle of the star. And in fact, when we get to the next stage, which is 0.8 years approximately, that's oxygen going to silicon and sulfur, that is actually below the timescale that it takes for things to propagate to the surface of the star. So we won't actually observe that at all. That is impossible to observe, and that is why we need simulations in order to understand what's actually happening there, because you never are going to know what's happening. But equally, it's important to know what's happening because you will see that stuff when the star explodes in a supernova at the end of its life. So that's kind of the reason why we do these simulations. So the final bit is, as some of you might know, is that we end up with an iron core in a roundabout sort of way again. It's not directly to iron, but you'd learn that if you did the course. And that's again via things like alpha capture and photon integration, and that takes us 0.02 years, or as I looked up a few hours ago, 7 days. So very quick indeed. These are really, very, very small timescales, especially with in terms of astronomy. So just to hammer that point home, mass, the initial mass, must be greater than or equal to approximately 8 solar masses to do all this. If it's less, we're probably only going to get to carbon burning. So if I get my pointer, so we're probably only going to get to about this stage here. We're not going to get to the central iron core, which is kind of characteristic of a massive star. So that's kind of how the two differ. Next, I'm going to show you this diagram. Now, it's not very easy to see, I admit, but it's a very helpful representation, I think. It's called a Kippenhahn diagram, and what it shows is, so the y-axis here, that's mass in solar masses. So this is a 22 solar mass model that's being run here. This is what we call time left. Now, it's the reason why we do log of time left, really. The reason why we use this is because it's the time it takes, the time between the end of the star's life, which is what we're interested in, and where we are now. Now, the beginning is very difficult to model, especially this kind of proto-star. It's just basically the model kind of fictitiously worming its way to the main sequence. It's not really the true thing that's happening. You kind of need a specialised model to do that. So what we do is we kind of just let it settle, and then it runs. And it runs towards the end, and the end at core collapse is kind of a defined point, so that's why we define it like that. And then you might know log 0 here, that's 1, so this is 1 year here. That's the main important point, because as I said before, 1 year is the time scale that it takes for information basically to travel out from the centre of the star to the surface. So if it's anything after 1 year in this region here, you're not going to see it. So things that you might see are the radius changing, but you wouldn't see the radius changing as a result of something happening in here, or indeed the temperature changing or anything like that, or the luminosity. You wouldn't see anything like that if something happened here. So that's why we need to model. Now these regions here. Now you might notice this very bright green thing. You can't read it. It says convection. And these are convecting regions. So in order to travel or to transmit energy, there's two main methods. There's radiation, so that's light, photons, and then there's three methods. There's radiation. There's convection. So that's you might think about, I don't know, your radiator on, and then the heat rises, travels across the room, and then falls and sinks, and it goes in like this convective pattern. That's the kind of thing we're talking about here. And then there's also neutrinos, which is important in this diagram. It's shown by the purple here. So this says net loss energy due to burning and a neutrino loss here. So you can see a lot of energy here is being lost by it's a net energy loss here, whereas the blue is a net energy gain. But anyway, back to these convective regions. Each convective region denotes one of these stages. So that's why I kind of talked through them. We got hydrogen burning, which is the first kind of region. They're very easy to pick out as well. It's quite nice. This is helium burning. They're very recognisable. Every model that you run will have this kind of thing in. And then we've got carbon burning, which is this bit here. I have to squint to see it. And then neon and oxygen burning. And those you might see here, they actually go off and they go up here. They go into what's called a shell. So carbon shell burning here. So you've actually got two things burning at the same time. And then we move on, and then we get to things like oxygen burning and silicon burning. as you get to the end of this model. And then over time we kind of build up this iron core, but you can't see that because iron's not burning. It's the end stage, if you will. Again, more physics I won't talk about. But anyway, there you go. So the next bit is mixing length theorem. What on earth is that? Well, mixing length theorem brings together all of these. You can't quite see it, but I will say what that says. All these different bits of physics. Again, physics I'm not going to go into because there's so much physics in this. But anyway, things like mass conservation, mass continuity, gravity, hydrostatic equilibrium, energy conservation, and others. You'll recognise at least one. Hopefully, gravity, for example. That's very important in a star. But equally, hydrostatic equilibrium is another thing you might know. That's the equilibrium between the pressure pushing out and the gravity pulling in, like the mass of the star, and that kind of interplay governs whether the star kind of grows or shrinks. But equally, all these others are very important. And we plug this physics in a roundabout sort of way to get these models to work. So this is mixing length theorem in a graphical form. It's very nice. So let me talk you through it. We've got this bubble here, and the bubble is a parcel, and when it rises through this column has got like a constant gradient. So it goes from a warm, a hot centre, and then cool. So it's what you'd expect with your radiator. You know, it goes from a hot place at the bottom, and the air rises, and then it goes around and it sinks. But as the air rises, eventually it's going to dissipate into the cool extremities of your room. So that's what we're showing here. It kind of dissipates here, and we can describe this using gradients. Here's a bit of maths for you. So this symbol here is called nabla, and that's a gradient. Okay. So I won't lose you, don't worry. Okay, so we've got it's change in temperature with respect to pressure. So this bubble here is at a constant pressure. Okay, so that's the main important thing here, and we're taking these gradients within the bubble itself and within the column, and we're using those to say whether or not. So the big question here is: does this bubble convex, or will the energy be transferred via radiation? And that is what the next slide is going to answer. So first off, we have these raw values. So things like opacity, which is kappa, that's this first one, or density, rho, gravitational acceleration or gravitational field strength, g, pressure, p, t is temperature, and cp is specific heat at a constant pressure, if you remember from your GCSE physics years. But anyway, it's an important property of the bubble. So there you go. Don't worry about it if you don't understand it. But the main important bit here, the main important bit here is these gradients. So again, all these upside down triangles, don't get worried about them. They're just gradients. Okay. So we've got nabla here, which is the temperature with respect to pressure at a given level. So that's within that little column. What's the value of nabla? Okay, and then here that's nabla prime. That's the temperature with respect to pressure within that element itself. So what's the gradient within? What's the gradient outside? Now nabla add. That's the adiabatic temperature gradient. Okay, so that's when no heat is transferred. So this is basically our little fudge factor to say, oh, I'm going to use the adiabatic gradient to describe what the gradient is within the bubble. So like some things that you don't know the answer to, you just use another value that's kind of using some assumptions. So here we're assuming there's no heat transfer. So that's the value that you get there. Nabla R, that's the temperature with respect to pressure for moving energy, but via radiation. So radiation, that's the other way that you can move energy instead of convection. So it's just kind of testing those things out. And then nabla mu here, that's the molecular weight gradient with respect to pressure within the element. Now that just means that it's basically looking at the different isotopes, or the different elements, or so things like silicon, sulfur, I don't know, what's the kind of makeup and where are they? That's what it's looking at. Or is the bubble homogeneous? So are all the elements spread out evenly? And that is what the next thing is going to explain. So we've got two criteria here. We've got this French guy, Ledoux, or this other guy. You might have heard of him, Schwarzschild. Okay, so they have their two criteria. So Ledoux is taking into account this kind of we call it heterogeneity. So like there is some stratification. There is some kind of difference between the molecular weight, between the distribution of these different things like silicon, sulfur, oxygen within this element. Whereas Schwarzschild says, oh well, it's going to be homogeneous. There's not going to be any of this. This isn't going to matter. So that is what I said during my thing. So we're gonna forget about all this scary molecular weight stuff, because why would you do that? So there you go. Next, time-dependent convection. So before we had a look at mixing lane theorem. Time-dependent convection is taking it like one step further, and it's looking at the start and the end of convection, and the start and the end are actually quite important. So this is kind of the dynamics of convection. The convection's got to start to grow when you turn your radiator on. It doesn't just suddenly go. It kind of builds up and then it goes. If you think about I don't know, some colourful liquid convecting in a glass or something, it has that strange dynamical flow to it. So that's the kind of thing we're trying to incorporate in time-dependent convection. And to do that, we're going to use this thing, fluid equations. I'm not going to show you them because they look disgusting. But anyway, we're approximating fluid equations in one dimension. What do I mean by one dimension? Okay, the one dimension here is radius. So it's from the middle of the star to the outside. That's the only dimension we're looking at. We're not looking at kind of stuff that's going around the star. That is three-dimensional. If I'm allowed to, there we go. You can kind of see it's very important in three dimensions. So how do I do it in one dimension? Quickly, does anyone know why I want to do it in one dimension and not three dimensions?
It's easier.
It is easier. It's quicker. Like I've not got all the time in the world, right? Like to do a three-dimensional model takes months.
Steal your supervisor as well.
Yeah, literally. It takes about 3-6 months to run one of these. It's a lot of computing power. I don't have that much time. Summer is not that long. Okay, so it takes about 6 days in comparison to run one of these 1D. I'll say 6 days. It could take anything from 2 hours to 6 days, but that depends on the resolution of the model. But I'll go into that later in this next section about MESA. Okay, MESA. What is that? Oh, what a weird word. Well, it stands for models. It's modules for experiments in stellar astrophysics. What does that mean? Okay, so modules. It's made up of different modules. It's a code basically, and it's made up of different modules, and all these different modules can simulate different things about the star, different bits of physics. So here I've got binary stars. It's a picture of binary stars from Varma. I'll have to illustrate my points. Next, it also has a module for asteroseismology. So that's just kind of small oscillations on the surface of the star. So it can simulate those. We've also got a module for stellar atmospheres. So what's going on in those? When I say stellar atmospheres, I just mean the kind of low density bits around the outside of the star. So it can simulate those. It can also simulate these, not me. It can simulate turbulence on the surface. Well, turbulence in general. But this is turbulence on the surface of the sun as an illustration there. I do like that picture. And it does this in this. Now, you might have heard of Fortran if you did coding in your youth. I've been told it's a very old thing to do. People are all in the Python, guys. What are you doing in Fortran? Well, in stellar astrophysics, we're all doing the Fortran. I'm sorry. Yeah, so there you go. But anyway, this is an example of one of these scripts that you use to basically it's where you have a list of variables, and then you can just set them to different things, and depending on what you want to do. You just tell the model, oh, I want to do this, and it will do it for you. You know, it's not that scary. Well, there you go. So things like here, you got this little variable, and then you just change it from true or false, and then it changes something about the model. So in my case, I was changing this little bit here. It says MLC underscore option. It's very important that you made sure that you. Sorry, Cox. Cox. This guy. So Cox is just is the original mixing length theorem in one dimension, whereas TDC, time dependent convection, somebody called Jeremy made an approximation to it in one dimension, because obviously time dependent convection is 3-dimensional, and that is what I was looking at here. I was looking at, is time dependent convection modelling convection more accurately or less accurately than Cox, which is the predecessor. This is like an update to the software, as it were, and I was investigating what kind of effects that had. To do that, obviously in raw form, I just get loads of scripts out at the end. They're enormous things. I can't download them on my computer. They are so big. And they're just loads of numbers. So how do I understand these numbers? Well, I use this little guy here. That's how you spell Kippenhahn, if you're wondering. So this is another Kippenhahn diagram, and here it's actually log of radius, because this is in some ways more interesting than log of mass, because you can kind of visualize the radius, and the radius is something that you look at in things like asteroseismology, as I said before. So this is where we kind of visualize what kind of things astroseismologists or people who look at stars through telescopes, actual real stars, would see the effects of, and we can kind of corroborate our models with real life using this radius. But anyway, this is one of the examples of a model that I ran, just to kind of show you what's happening here. So here's our hydrogen to helium convective cell. Here's our helium to carbon. They're really obvious. You can see them properly here. Carbon to neon and oxygen, that goes into a shell here, and then neon to oxygen, that goes into a shell. Oxygen to silicon and sulfur, that goes into a shell. So that's your oxygen burning shell there. And then finally silicon goes to iron, and that goes off into a shell. And then we get our core collapse, which you can't model because the model isn't that big. Why would we need to do that? So kind of, the model kind of stops. It's like core collapse, no, not doing anymore, at the very end. And the other way that we do that, so that was a general view. We're not always sure, is it like carbon burning there, or is it something else? What's happening? Why is this big? Why is the radius suddenly increasing? So we need to kind of visualize that better. What we do is we use these things. They're called abundance plots. Now, the colours here are atrocious, and you can't see what is written there. So I will quickly run through it. So this, as I said before, we have these three types of stars: population 1, 2, and 3. Okay, remember that. And they're to do with metallicity. Okay, so if you write in your code, my star has this metallicity. It will that's not 0. It will add some of these elements here to kind of represent that. So these are all the elements that haven't been generated by this star. They've been generated by the previous star or stars that gave birth to that exploded in this dust cloud and then reformed into a new star. Here we've got helium and hydrogen. So those are the main things. Here's abundance on the left. This is a log scale, so we've got 10 to the 0, so that's 1. And then we go all the way down to 10 to the minus 7 here. And then we've got mass here. This isn't the whole mass. This is just from 0, so that's the core, all the way, or around the core, it's not quite 0, all the way to 7, which is less than halfway through. I say that mass is approximately proportional to radius, but it's not quite. So remember, this is a 20 solar mass model. Okay, that set the scene. Also here, some helpful numbers if you can read them. Log of age, that's log of time left. So currently we're on 16, so very early on. And then we've got model number here. We're already on the 2870th model in this simulation. So simulation is made up of many models, and we'll see soon how many models it's made up of. It really varies. But anyway, let's run this. Okay, so what's happening? Oh, okay, watch it. Watch the lines. Nothing's happening at the moment. Oh, okay, what's this black line? It's temperature. So we've also got temperature on the right here as well. Oh, and stuff is happening. Okay, now the main thing here, you saw hydrogen. Yeah, hydrogen's gone down and helium's gone up. It's actually zipped off the graph. It's gone that far up. So that's what's happening. So what you saw there was hydrogen here that was burning, that went down, and helium went up. That's what you'd expect. Okay. There are a few other things that's happening because of the metallicity. The metallicity is why this isn't just a simple thing of saying, oh, hydrogen goes to helium. It's more nuanced than that. And then remember, watch this temperature gradient here. Temperature is rising, it's rising, and then we've got this helium's now going down, carbon's gone up, and oxygen's gone up. Now remember, it was helium going to carbon and oxygen, so that's what you'd expect. So that it's a CNO cycle. It's called CNO for a reason. Carbon, nitrogen, oxygen. But anyway, so you've got this helium. It's dropping off. Remember, this is the core, so the helium is being pushed. This is showing it's being pushed to the outer regions of the star. So the helium just kind of being displaced, and it's also reducing in what we call abundance, the amount of stuff relative to other stuff. It's a percentage as opposed to there's 10 solar masses of helium or so. And then again, this temperature is increasing. So as evolution continues, temperature always increases. Okay, temperature increasing more. Carbon is now going to neon and oxygen. This is carbon. Look at that, it's going down. And neon is increasing, as you would expect. But you can see here there are very distracting things that are going on, aren't there? Here it suddenly drops off. It's what we call a shell. So this region here, you've got kind of sudden drop off, and then you've got sudden drop off here. That denotes a shell region. So that's another important thing to understand about these, but I'll show you a bit more about those later. Next, okay, so we have neon going to oxygen, and then a bit later on we've got oxygen going to silicon and sulfur. So here's neon, that's decreasing there. Oxygen's got a bit of a bump here, so it's increasing slightly in abundance. And can I find silicon and sulfur? Oh, no. They're somewhere in there. Anyway, trust me, that's what's happening. Okay, but as over time, it actually gets more and more complicated here because of the metallicity. So you can see metallicity actually gets more and more important as you get further on in evolution. It kind of, all this interaction, it all looks very complicated. So back in that model that I showed you with the shells, we call it an onion skin model. It doesn't look like that, does it? You know, that is very, very complicated, and it kind of shows you the nuances and the interactions that are happening. And that's why stars are so difficult to model. So there you go. Next, we've got this. So this is silicon going to iron. So I think iron is somewhere in here. Oh, there we go. Iron 56, just there. That's the probably pink line that you can't see. And then silicon is somewhere in there as well. But the point is that you can see, especially towards the core, iron is increasing. So you can kind of understand what's happening here from just from the diagram. Now I'll draw your attention here. 24,290 models. That wasn't the highest number of models I ran for a simulation. And then minus 10 of log age. So that is less than a year before core collapse. Okay, so I looked at all my pretty diagrams. I looked at even more pretty diagrams, I have to say, starting with this one. This is what I promised you. It's a Hertz and Russell diagram. If you've not met this, if you've not met a Hertz and Russell diagram, you've not lived. Okay, so this is a graph of luminosity by surface temperature here. So it's is it log? Yeah, it is. There we go. So log log of luminosity by log of surface temperature. And these are the numbers that ping out of the model. Literally, it's a column, it says temperature, you steal that column and then you plot it in Python. You can see here we've got pre-ZAMs, that word again, pre-ZAMs, pre-zero age main sequence. This is why we say ZAMs. We say ZAMs because it is a very obvious point in the HR diagram. It's this little flicky thing that looks, well, it literally is. You look at that and you think, oh, ZAMs. So you see that now. It shouldn't really do this. This is a fictitious thing about the model. That there are some very strange things that the model does that aren't true to, like, physically true. So that's why you need a bit of physics background in order to understand what's real and what's really not in the computer. The computer doesn't do everything correctly, and this is a really good illustration of that. Now, I ran two different types of model. I ran, so as well as comparing Cox, so that's mixing layer theorem without the fluid stuff, and then TDC, time dependent convection, that is the mixing, the convection with the fluidy stuff, or the approximation in one dimension. I also simultaneously looked at the difference between fine and coarse. So when I say fine, I mean high resolution, so lots of models, ages to run, 6 days or whatever, annoying but true. Or coarse, which is much nicer, it takes about 2 hours to run. Those are about 4,000 models maybe. You can see here, you probably can't make out, maybe you can. So the colours here. You've got red and, what was that, blue. So these here at the top, those are fine models, whereas the bottom here are coarse models. And what you can see here is that the coarse and the fine are very different. Why is that? Well, it's because it's not resolving the same kind of things that are happening. And over time, so time kind of goes this way. So all the stuff here that wasn't helium or hydrogen burn, all this stuff is very quick. It just kind of zips up, and all this stuff it kind of exaggerates the difference between coarse and fine. But what I was looking for was, well, is there a difference in evolution between time-dependent convection and Cox? And well, it's definitely not as big as the difference between fine and coarse. So yeah, you don't always get where your technology wants to work with me. Here we go. So that zip, that's a shell merger. So that's things like chromium and something else. And then you can see helium that's being brought up, and that's a common thing that we saw in lots of different models, and in other models as well that other people in the group that I was in ran. So little interesting thing that I thought I'd show you there. Another shell merger. This is a shell merger that you can actually see in the star, so like on a big scale. So I'll show you that bit in a moment. Again, look at this number here. So this is log of 8. So that's pre 1 year. So you can see this on the surface. So I'll show you it being seen on the surface. But this is a shell merger. So watch out for that same event happening. Okay. And look at this black line here as well. See what happens. So you can see here it's kind of moving along, and then suddenly this zip happens, and it's carbon, neon, oxygen, magnesium, that kind of thing that's interacting here, and it's making this kind of shell in the middle. And you can see here this bit here is the temperature, and you can see that there is a sudden temperature gradient at the edge of this shell. So if I show you why, okay, this is a zoomed in Kippenheim diagram. We love these, okay? So we've got time-dependent convection here, so that's the new physics, and then Cox, that's the old one. And you can see they look different. This is log of time left, so this is negative, so that means it's after 1 year, okay? And you can see here, suddenly, at this point, this is when the shell merger happens. At the same point, we see this big bubble, this big kind of increase in radius. And these lines here, these are actually lines of mass. So you can see here that when the mass when these lines that denote what mass is below them, they start separating. So it means that it's basically showing it's much less dense. And in fact, on the surface here, if you zoom in here, now at the moment it looks kind of flat, but actually if you zoom in, you'll be able to see that there is a big jump in the radius as well. So this is something that I've modelled in both models. Now they're slightly different, but if you look at the timescales here, maybe it's just because of some small difference earlier on in evolution. Not sure, yeah, you can see that the actual that this event could be observed by someone on Earth and then corroborated with this model if it's true or not. Okay. The other thing I did, equations. Okay, so the top one here is one that it's like the traditional way of calculating central velocity. So v is velocity, v squared, velocity squared. Okay, convective velocity. Right. I hope you're with me. Okay, I'm not going to talk through the whole equation, don't worry. So the top one here is from Maeder et al. 2009, and it's used to predict the convective velocity for mixing length theorem. So that's the one without the fluid equations in one dimension. And then the bottom one, it looks very different to the top one, apart from the very first thing. Okay, but actually it's at long time scales. Yes, at long time scales. So that's early in evolution. Early in evolution, the bottom one approximates to the top one, or at least it should, okay, in theory. So that's kind of what I'm looking at. And the reason why I say that is because early on, you've got hydrogen, helium, it's long time scales, not much is happening, we don't really expect the two to differ. Whereas later on, time-dependent convection is expected to get more and more important, so there should be more and more difference between the two. Okay, so this is another scary diagram, right? So this is at 35% helium content. So that is at a very early stage in evolution. So we should expect that Cox and TDC, that this thing without fluidy stuff and the thing with fluidy stuff are similar. Okay, and again, and here the two things I've actually differentiated are the number that's been spat out of the model and the number that I spat out using the equations I just showed you, or specifically the easier one to do, which was the top one. So yeah, now if we focus on the dashed line, so that is for this is velocity. The solid line is for Mach number. That's velocity divided by the speed of sound. If you can't think about that, don't worry, I'm not going to look at it. So here, if you think about the dashed here, you can see all the lines kind of track all the way. So if you look at here, this is mass, this is the centre of the star, so they track all the way up to here. In the very centre, when these all go down and this one goes up. So it shows you the very centre of a star. It's actually really difficult to model things because its radius equals 0. It's kind of this little bit in the middle. Like how do you work with that? And evidently, something here. This is this number that's spat out of the Cox model, the bit without the fluidy stuff, is different to everything else. So I don't know what's going on here, but there you go. Interesting thing. Again, in science, you get a lot of weird things and you can't explain them. It's what we're all about. Okay, and then some limitations to the project that I did. Well, for example, here you can see some diagrams, and you look at these and think, "Oh, exciting things are happening," but is it the model that's doing this? Is it the computer that's dreaming? Or is it actually a really cool thing that I've discovered? It's probably the first, but For example, here you can see this kind of oscillation, this weird wibble wobble that's kind of getting bigger and bigger, and you're like, oh, what's that all about? And here you can also see this sudden shell merger that I showed you before. It's actually a different. It's a similar thing that's happening at a similar time, but it's kind of looking a bit different. But you can't really see this thing going on here. Well, actually, it is going on. Okay. If you zoom into the radius, you can see You can see, so the red here, so it's this line here, is fine. So fine is high resolution, a long time to run, many models. And coarse here, so that's, fine here again. So that again, same thing, but one's Cox with the fluid, without the fluid, and then one is TDC with the fluid equations, or the approximation to. Okay, and then these are the coarse models. So it's showing you here, this effect is only seen in the fine models. What? It's not changing the physics, it's just changing how many models I'm running. So it shouldn't really be happening. But these kind of things, what are these physical things or numerical? I can't tell. Just to point out here, this is log radius, but it's got no scale. So when you see these kind of weird things happening here, it's not because suddenly the star's going crazy. Anyway, so another thing is time. As I said before, time. Well, like even 6 days, it's dreadful. Here I sat at my computer typing screen space -r space model 20 enter, still running. Control C. Oh. Anyway, yeah, very, very, very annoying. I find myself typing that all the time. In fact, I typed it so much I can auto complete in my coding thing. If you know anything about terminal or coding, you'll know what I mean. It's very distressing. Is it ready yet? No, it's not. It's failed. Anyway, that's the joy of modelling. And then a quick bit just to talk through what can be done in the future. Obviously, I've brought up many things that weren't explained, and what are the reasons behind those. But some things that are more interesting as well, generally, are to actually compare these 2D models. So this is an example of a TDC, so with the fluid equations model, and this is that 3D model. It'd be interesting to compare the outcome of the 3D to the 1D even, and then actually see kind of how similar they are or how different. Does the approximation to 1 dimension actually represent at all what's happening in 3 dimensions? So something that's not been looked into yet, and something that would be interesting to go back onto the other slide. Has anyone got any questions? This is my beautiful bibliography. If I just